Lionel is going to tell us how to decouple resolution from type inference.
Thank you. All right. I'm very happy to talk here at one of my favorite workshops, and it's good that now that everyone has left, we can start talking about language design at the Programming Language Conference, right? So, yes, it's a programming language conference, but that was just a joke. Okay, so yeah, the talk is entitled "Decoupling Resolution from Type Inference: A Language Journey from MScript to WIT." So you'll see what I mean by this slightly pompous title very soon. So first, an introduction. What does this mean? And you may recognize a syntax similar to JavaScript syntax, where we have a lambda that binds a parameter x. Okay. And okay, and it accesses the field foo in x and adds 1 to it. And obviously, there's not just one answer as to what this means, right? It could mean different kind of things depending on what foo is and what sort of addition you're using. But the simplest answer is provided by dynamic languages, because in dynamic languages, there's just one very general answer, which is that this is a field access which is performed at runtime dynamically, followed by a plus operation, which is dynamically dispatched. So it will inspect the type of the operands at runtime and then figure out what to do, which may or may not be sensible depending on the semantics of the language. Now, note that this dynamic language interpretation of the program is not incompatible with static typing, right? We can give various types to this program that reflect its runtime semantics. So here's an example of a type we could give it, assuming we have some form of structural typing. We're saying here that the parameter x has a field of type foo, named foo of type a record, which has a plus operation on it that takes an int and returns a, and the overall lambda returns an a. Okay, so I just wanted to make this distinction very clear that dynamic languages are not incompatible with static typing. And so this is nice because the semantics is unambiguous, but it has many downsides, right? Because this has some runtime overhead. You're doing dictionary lookups at runtime just to access normal fields, which may not be desired. And it excludes, this interpretation of terms excludes many nice features that you may want to have, such as type classes, right? Or implicit parameters, extension methods, etc. Because these rely on some form of type information being known by the compiler in order to be compiled successfully. And so, on the other hand, we have static languages, which may ascribe various different semantics to this piece of program. And the semantics is actually context dependent. So what this means depends in which place you put the term and how the compiler ends up figuring out what foo is and what addition is, right? This typically leads to better, more efficient implementations, but it's also more complex and sometimes less predictable. And here's an example type, proper static type we could infer for it. And so there are all sorts of kind of ambiguities that the static compiler must resolve, such as ad hoc overloading, which may happen if you define several functions in the same scope that have the same name, but different types, or if you import two functions with the same name into the same scope, right? And type classes, also called traits in languages like Rust, implicits, which is the general term I use for both implicit parameters and implicit function types. I will give an example of that later. Implicit namespacing, which is a feature I'll exemplify later as well. And of course, field selection, which is the motivating example. Does this make sense to everyone? Don't hesitate to interrupt me because the talk is a bit out there, so if you don't agree or if you're not following, please let me know.
There is a dual to field selection, which is constructor disambiguation.
Yes, yeah, you're right. So yeah, I could have put it in this list. Good point. So it's well known by most compiler implementers that the more complexity you put in a type system, the more resolution of these kind of features turns out to be usually, right? Because if the type system starts incorporating things like subtyping, then it may no longer be very clear or very obvious which overload of an overloaded function definition you're trying to use, right? And in the general case, compilers might have to do backtracking, or they might have to work very hard, right? And nowadays, type systems are actually getting pretty complex, right? Pretty advanced and expressive. So we have, of course, dependent types and all sorts of structural typing with Boolean connectives like unions and intersections. We also have liquid types with refinement types that are backed by SMT solvers. And of course, it's not cheap to type check such terms. And it has a lot of complexity, so it compounds with the complexity of overloading and resolution. So I think resolution is actually one of the very important aspects of language design that's almost never discussed or very little discussed, which is a bit funny because it influences so many things, right? For example, it's the main reason why type inference for object-oriented programming is quite hard, right? So some may think that inheritance or subtyping are the reasons why type inference for object-oriented programming is difficult, but that's not really the case, I believe. The real problem is that when you're calling a method, you need to know what you're calling because the method might be polymorphic, or it might have the compiler very often needs to know exactly what method is calling in order to properly compile it, right? Make sense? Yep. Let's move on. So, so what if we separate this kind of resolution from the process of type inference and type checking? And the idea is to separate these two into one sort of static analysis, which is aware of the types, and which we look at the program in a very basic way, without trying to reason too much, right? Without trying to figure out exact types. And later we can do the full type checking pass if we want to, or maybe we can do it in parallel with running the tests, or it's basically optional, right? After you have done the basic static analysis, you can compile your program, and type checking is now just used to make sure that the program is correct, but not to compile it, right? And the goal is to make the runtime semantics very simple, stable, so that subtle changes to the type system or type inference will not affect the runtime semantics, and predictable for users, so that they have an easy mental model. And the goal is also to make it easy to compile and efficient to compile, so that the compiler doesn't have to work very hard to actually compile and run the program, which may be very important for use cases where fast compilation is important, such as for interactive applications like video games, where you want a quick compilation and running cycle, right? So another benefit we get from this is that the semantics of the language is no longer tied to a type system, right? So it lets you plug in various type systems and customize your type system. Basically, all the type systems have to agree about the basic semantics of a program, which is given by the static analysis. Static analysis says, this is the overload that's resolved, deal with it, right? And then the type system can add refinements and all sorts of stuff on top of that. It should simplify the evolution of type inference. For example, if you tweak a heuristic somewhere to help type inference go through, it's not going to suddenly make some programs stop working. Mm-hmm.
Yeah, this is confusing.
Type aware yes. Input. Okay, yeah, I'm gonna get to it. It's a bit subtle. So yes, thanks for asking your question. Yes, it's confusing. All right. I see that. So what I want to say here is that this is not such a crazy idea, right? So if you think about it, this sort of stratification is not unheard of. There are many examples of such things. For example, say in liquid Haskell, you do a normal type checking pass first and type inference with normal Haskell types, and then you refine the types with subtyping and perform some SMT checks, if I'm not mistaken, right? And so something similar happens in F-star and in Scala for its previous liquid type prototypes, but apparently not the upcoming one, as we'll learn later. And Rust is the same for lifetimes, for example. So Rust infers and checks lifetimes separately from type checking and type inference. And for example, lifetimes cannot participate in the resolution of type classes. So it's a completely different phase, which the Rust designers designed this way because it decouples things. It allows each thing to be simpler on its own, right? Instead of trying to do everything together. Trait resolution and type inference is already complicated enough. They didn't want to add reasoning about lifetime in addition to that. We have a similar, yet another example with the Scala 3, which does normal type checking, if I am not mistaken, and then checks things like capture tracking afterwards, after type inference. Okay, so basically what I'm proposing here is just to take this idea a bit further, actually to take it to its extreme, where the first phase of type inference is not meant to check any type, is just meant to compile the program, and then you do all the complicated stuff later in the second phase. So I come to this MLScript and WIT, which I'm going to describe now. So these are two names of languages. And basically, MLScript is the language we started developing in my research group, whose core value proposition was to be a better TypeScript. So that means it has a sound type system, which is structural in the spirit of TypeScript, and it also used constraints-based type inference, and has an emphasis on functional programming and expressive pattern matching features. And basically, we really strived to make this really a better TypeScript with following the TypeScript philosophy, which is optional typing. So in TypeScript, types are really just checked documentation that do not affect the program's semantics, right? So you can just remove the types from the TypeScript program, and the program behaves exactly the same. And this is also known as a char-style or extrinsic semantic of types. And so we developed this MLScript language, and it works. It does what it needs to do. But we really wanted something like type classes and extension methods because they're so convenient and they're safer than the dynamic counterparts. So we were kind of stuck, right? We found actually we do want a little bit of taking into account the types in order to inform the runtime behavior of the program. So that's where we were when we came up with a new language idea. So the tentative name is WIT. And so the goal of WIT is to use hybrid resolution, which is the approach I just described, right? Where you do basically a first pass of static analysis to compile the program, and then you do the real type inference. And so the main assumptions we use is that the definitions that are exported from a module are normally annotated with their signatures. So this allows the analysis to be modular, right? You don't have to do a whole program analysis. You can always start from the signatures of the members you export. If you do not annotate a signature, nothing bad happens. It's just that you're not going to be able to resolve things that are related to the unannotated parts. Moreover, we assume that local functions that are not annotated or local definitions do not need to be polymorphic in their resolution. And this is in order to make the static analysis very scalable and efficient, so it doesn't have to do things like generalization and polymorphism. So, right, and so the main mechanism is something like control flow analysis, which is basically the same as subtype inference, without implicit generalization to avoid exponential behaviors. And the reason I call this a static analysis and not a type inference is because it never reports an error to the user, right? So even if it finds things that look problematic in its point of view, it may just be that it's too approximate, and so it's not seeing that the program is actually correct. But the bug will be, if there's a bug, it will be caught later by the real type checking and type inference algorithm. So the goal of the static analysis is just to figure out, do a best effort to figure out what resolution to do, and the actual type checking will be done later. Well,
So what do you do if you don't know how to resolve something?
yes, then it's a compilation error, and the user has to.
So you report something.
Yes. Oh yeah, right. You're correct. Yeah. So we do not report flow errors like type mismatches, but we do report a lack of information that prevents us from doing a resolution. That's right. Or too much information that would make the resolution ambiguous. All right. And so in the worst case, yeah, so we get a compilation error. So this is the traditional example of a type class that's ambiguous, where you try to read a value from a string and then show it immediately. So it's ambiguous which type class instance you're meaning, and that's an error. But this one, which has a type error, actually compiles, right? It resolves the instance correctly because it has all the information it needs to resolve the instance. And the fact that we are trying to negate the output of the show method, which is a string, will be caught later by the type checker. Okay, I think I need to speed up a bit. So here are some other examples. Because we assume that functions are monomorphic in their resolution, you can call a method such as foo here, which uses a type class. As long as you always call it with arguments that induce the same type class, it's fine. But if you try to call it with different arguments, then you get an error. And you can fix this error by explicitly saying, oh, actually, I do want this function to be polymorphic in its resolution, which requires a type annotation. And so this is reminiscent of let should not be generalized, this observation made in Haskell, where they found that let generalization caused all sorts of problems, except that we can still generalize let bindings, because we can still do that during type inference later, and it doesn't interact or messes with resolution anymore. And so here's an example of where the analysis has to make some approximation because it doesn't want to do backtracking, it doesn't want to do any complicated reasoning. And so if you have a method that is dynamically overloaded, meaning that it's resolved at runtime, we can still give it a precise type using an intersection type. And if you use that method only with arguments of type integer, then you will only get integers out, because the static analysis is smart enough to filter out the case that's not use of the intersection. But if you pass both, say, booleans and strings to the function, as in the example below, then the type will be approximated to this much less useful type, which is still useful enough to do flow analysis. And so the program below still compiles, even with the more approximate type, because we will not report type mismatches, right? So the flow analysis thinks there's a type mismatch, but there's no actual ambiguity in the resolution, and so this works out. And here's a cool feature that we can have in the language based on this approach, which is implicit namespacing and extension methods. So say we have a shape type, which is defined as a union of several other types, which are defined in its companion module, so the module that's associated with the type. And we have some helper functions defined in the same module. Then these helper functions become available to the shape type, so that they can be used using the dot operator as methods. So for example, if you write this program, the fill method will be resolved because we know the shape, that the binding shape receives a circle, a shape at runtime. So we know this based on the static analysis. Moreover, we have this lead-in dot selection shorthand, which allows us to omit prefixes when they can be inferred from the context. So we know that red is a color, so we'll look for the red constructor in the color module automatically. And we can do the same for shape. So if we know that what we want is a shape, we can just write dot circle, and it will look for the correct constructor module, the correct place where the module is where the type is defined. And
Small shape is big shape.
mhm.
The type of small shape is so
Yes,
circle gives the shape.
the type of this is big is shape, right? Mm-hmm. Oh, so yep.
Circle returns a shape.
Sorry.
Circle returns a shape.
Yes, a circle is a kind of shape because a shape is just a union of circle and other things, right? And so both of these shorthand programs are equivalent to the fully desugared program, which doesn't use any special features. Okay, I don't think I have a time for a demo, but trust me, it kind of works. So actually, it's good that I don't have time to give a demo. But other things we want in the language as well are things like traditional overloading and type classes, as I mentioned. Also implicit parameters, which let you pass contextual things, such as the context in an evaluator, and implicit function types, which let you implicitly abstract over things like contexts. So it's like the dual to implicit parameters. And there's a few papers about it in the context of ACDA and Scala 3, if you're interested. I think I should probably stop here and answer any questions you have. So I'll finish with the conclusion slide. Do you have any questions? Yes.
So you're working in a really permissive language that, I mean, you said, you make the statement, you say, we only need types up to the point that we can compile the program. But you're working in a language, ML script, that it seems like is extremely permissive at runtime.
Well, it's no longer ML script, now it's WIT, but the goal is to compile it to WebAssembly, which will be much less permissive.
Well, I wanted to ask, I mean, can you say a little bit about like taking some of the same ideas and applying them to a more traditionally, ahead of time compiled language and for example, there's a lot of situations where you want the type to actually inform how you represent the type in memory.
Yes, we definitely want to do that. So this is completely compatible with this notion, right? It's just that you're not necessarily going to be able to do as much with, say, for example, you want unboxed integers. You're not going to be able to take the union of an unboxed integer with arbitrary data types, for example. So you can ensure that during compilation based on the static analysis.
Like what? You have this phasing of you check this and then you check this. And then
Yes, the static analysis figures out how to compile things. So it will figure out what's the calling convention and memory representation of all the values that flow in the program.
Yes, let's take one more question of the speaker switch.
Yeah, so you motivated why this could be nice. Do you have an example? I mean, there must be examples of weird error messages you get as a result of not reporting early enough.
Yes. I don't know. Are you thinking of something specific?
No.
I guess the weirdest error messages would be something that when it finds several possible solutions, then it just reports all the solution. It says it's ambiguous what you mean here. The selection here could be desugared into different module methods.
Have you run into issues using it?
Not yet.